All right, everybody, so welcome back. We are starting chapter 3, in which we learn about linear and quadratic functions. So let's get into it with section 3.1. Okay, we're going to learn properties of linear functions and linear models. A lot of this should be pretty familiar to you. Okay, we want to learn how to graph linear functions, which is actually something we've already covered. Learn about average rate of change to identify what linear function is what. Determine whether linear functions are increasing, decreasing, or constant, and build linear models. And again, this is actually all stuff that we've touched upon in earlier sections. We're just bringing it all together here. Okay, so a linear function is just something of the form mx plus b, where m is called the slope and b is the y-intercept. There are other ways to write linear functions or lines. Point-slope form happens to be my favorite. This one here is called slope-intercept form. Okay, if a function isn't linear, it's called nonlinear, not the most complicated definition. All right, so consider the function f of x is 2x minus 3. Can we determine what the domain and range of f are? And to remind ourselves, the domain is every value of x that can be plugged in, and the range is everything that it is possible to get out. So take a moment, try to answer for yourself, what are the domain and range of f? Okay. So this is a linear function with slope 2 and y-intercept negative 3. We see that just from the 2 and the 3, the minus 3 right there. Okay. So if we want to graph the function, we can plot any point we want. However, the intercept right here, the intercept right there of negative 3 means that this point definitely belongs to the line. Okay, and then we can just draw a line with slope 2. And remember, slope 2 means if I go over 1 unit, I have to go up 2 units. So if you plot a point 0, 3, you would then have a line with that sort of slope. Okay, so here is a graph of that line. So they started with the intercept of 0, minus 3. Then did this over 1, up 2 business to plot a second point, and then draw the line connecting both of them. And the domain and range are both all real numbers. There is any number you want, you can plug in. Any number you start with, you can multiply by 2 and subtract 3. Remember, for most of our purposes, for now at least, the only restriction to a domain is you can't divide by 0, and you don't want to take the square root of a negative number, but we're not dividing by anything, and there are no square roots here, so the domain is everything. The range is also everything. Now, you can actually see this visually. This line is going to keep going up and up and up, so no matter which y value I want, eventually the line will reach any y value I could possibly pick, whether it be positive or negative. There's another way you can see this. Okay, so pick any y you want. So it could be 1,000,000, it could be -2, whatever. Any y value you're hoping to get out. Then we have y is equal to 2x minus 3, which means y plus 3 is 2x, which means x is y plus 3 over 2. So if I want to get out a particular value of y, if I just start with this value of x, I will get out this value of y. And there's no reason I can't start with my given value of y, add 3, and divide by 2. Any number y you want, you can add 3 and then divide by 2, which means you can pick this x, which means you can get out that y. So any number y you want, it's totally possible to get it out. Okay. This is now just saying an alternative way to graph the function would have been to pick any point you wanted and then draw a line of slope 2. There's nothing particular about the intercept. You could, for example, let x equal 2, and then you would have y is equal to 2 times 2 minus 3. That's 1. You plot the point 2, 1, and then you could do let's go over 1 and up 2, and you would get, well, if x equals 3, then y is equal to 2 times 3 minus 3, which is 3. So you go ahead and plot the point 3, 3, and then you draw the line connecting them, and you'll get the same graph. Okay. The slope of a line, m, and remember, this is stuff we've discussed, m is rise over run, also called the average rate of change of the line. Okay. So the slope of the line is its average rate of change. So can we use the average rate of change to identify certain linear functions. So in this example, we've got bacteria. It's placed into a Petri dish, and it's allowed to grow. So after a given number of hours, we can measure the population, and we can call that x, hours, population in grams. Okay, so here is a chart of data. So plot these points, and then determine the average rate of change and determine whether or not this is a linear function. Okay, so if we start plotting these points, and I'll just go back to the previous slide, so these are the points we are plotting, 0, 0.01, 1.04. So here's 0, 0.01, 1.04, and so forth, okay? And we plot all the points on that curve. Notice it doesn't really look like a straight line is going to join these up. And indeed, if we start trying to compute average rates of change, okay, we can't draw a straight line through all these points. And if you computed, for example, rise over run between these 2 points, rise over run these 2 points, rise over run between these 2 points, you'd be getting out substantially different delta y over delta x's. In real-world scenarios, you wouldn't expect things to line up perfectly. So if something is a line, it might look something kind of like this, where sure, this is a slightly different slope than this, is slightly different from that, but they're fairly close to one another. Here, the delta y over delta x's that you'll get are very, very different. If we go back to the page with the data on it, okay, here, for example, okay, I would have delta y over delta x. I'm just going to be approximate, okay? I'd have 7.82 minus 2.1. That's about 5.6 something. And the delta x was just from 5 to 4, which is 1. So this is about 5.6. However, if I go all the way back here, I'd have delta y over delta x. Now my delta y, I take the difference of the two y coordinates. 0.04 over 0.1 is 0.03. And delta x, 1 minus 0, is still 1. This is 0.03. These are way different. Okay. 5.6 is vastly larger than 0.03. So there really isn't a constant rate of change. And remember, a linear function is one with a constant rate of change. So this is not a linear function. Okay. So here, if we go through and compute a whole bunch of delta y over delta x's, we see that they are very different. This is the same example, the same data. So the function isn't linear because delta y over delta x does not stay the same or even close to the same. In fact, delta y over delta x kept getting bigger. Okay, if we go back here and look, if I just compare these 2 points, we got this for delta y over delta x. If we just compare these 2 points, we got this. Notice that delta y over delta x is always getting bigger and bigger and bigger. So the slope keeps getting steeper and steeper and steeper. And that looks like the picture we saw. So not only is the population increasing, the rate at which the population is increasing is itself increasing. Okay? The population's getting bigger, but how much it's getting bigger is also getting bigger. And now we're talking not just about how things are changing, but how the way things are changing is changing. And that's really setting up what calculus is well-primed and well-suited to discuss. Okay. So let's do one more example in this video. So here's a chart of data. Okay, we've got how much soda can be bought and how many hot dogs can be bought. So for example, based on how much money this person has, 60 bucks apparently, they can buy 20 sodas and 0 hot dogs. By the way, what does this tell me the cost of a soda is? That's right, 3 bucks. Okay. On the other hand, they can buy 15 sodas and 3 hot dogs. Since we already know, by the way, that sodas are $3 and we have 60 bucks, if I can buy 15 sodas and 3 hot dogs, then what does a hot dog cost? Well, if sodas are 3 bucks, 15 of them is $45, which leaves 60 minus 45, $15 remaining. So I can buy 3 hot dogs with 15 bucks. I can conclude they probably cost $5. So I've got $3 sodas and $5 hot dogs, and here are some various combinations of items I can purchase, and we're just going to plot those as points. Okay. So if we plot these, is this a linear function? Well, here's the various points plotted, And if we compute delta y over delta x, comparing the first two values, okay, I have the point 20, 0 right here, and here's the point 15, 3. Whoops, sorry, 15, 3. And if I take these, then my delta y is 3 over 0, and my delta x is, sorry, 3 minus 0, and my delta x is 15 minus 20, which is negative 0.6, which they've identified. And if we do these 2 points, you can also compute a negative 0.6, and we do these 2 points, we also compute negative 0.6. Okay, so what does that tell us about the rate of change? Well, the rate of change, delta y over delta x, looks to be the same over and over again, so the function is linear, and these points do lie on a straight line. Okay, so when we come back in the next video, we'll talk about increasing, decreasing, and constant linear functions.